There is a place in our universe, hidden in the vast expanse between galaxies, where the very fabric of reality might be coming undone. A region so mysterious, so profoundly strange, that scientists have only just begun to understand it, and they're calling it the Cosmic Anvil. Picture this, a silent, invisible forge in the depths of space, where dimensions themselves could be collapsing, bending the laws of physics in ways we can barely imagine. It sounds like something from science fiction, but what if it's real? What if, right now, the universe is hiding one of its most extraordinary secrets in plain sight? Think about the night sky for a moment. All those twinkling stars, distant galaxies, and cosmic wonders we've grown so familiar with. We look up and feel a sense of awe, but beneath that beauty lies a deeper mystery, one that challenges everything we think we know. The Cosmic Anvil isn't just another scientific curiosity. It's a window into the hidden workings of reality itself. Some researchers believe it could be a place where dimensions overlap, where gravity behaves in bizarre ways, and where the universe might literally be folding in on itself. If that sounds mind-bending, that's because it is, and it's exactly why this discovery has sent shockwaves through the scientific community. You're about to embark on a journey into one of the greatest enigmas of our time. This isn't just a story about far-off cosmic phenomena. It's about our place in the universe and our endless quest to understand it. Together, we'll explore what the Cosmic Anvil could mean for the future of physics, for our understanding of space and time, and perhaps even for the ultimate fate of reality itself. So settle in, open your mind, and get ready to dive into a mystery that's as thrilling as it is profound. The universe has always had secrets, but this might be its most astonishing one yet. So what exactly is this Cosmic Anvil? To grasp this idea, we first need to think about the very nature of our reality. We live in a universe with 3 dimensions of space and one of time, a stable, predictable framework that allows planets to orbit and life to exist. But imagine if that framework began to crack. The Cosmic Anvil is theorized to be a specific point in spacetime where this cracking is happening on a monumental scale. A place where the boundaries between dimensions are not just thin, but are actively breaking down. Think of it like a geological fault line, but for reality itself. Just as immense pressure deep within the Earth can cause tectonic plates to shift and collide, creating earthquakes, certain extreme conditions in the cosmos might generate pressures so profound that they strain the fabric of dimensions. The anvil part of the name isn't just for show. It evokes the image of a cosmic forge, a place where the fundamental laws of physics are being hammered and reshaped under unimaginable forces. It's not a physical object you could see or touch, but rather a region of spacetime behaving in a way we've never witnessed before. One of the most useful ways to understand this is by comparing it to phenomena we already know, like black holes and white holes. A black hole is a point of ultimate collapse where gravity is so intense that not even light can escape. A white hole, while purely theoretical, is imagined as its opposite, a point where energy and matter are constantly erupting outward, a fountain of creation that nothing can enter. Now picture a black hole and a white hole colliding or existing in an unstable, intertwined state. The region where their incredible forces meet would be a maelstrom of conflicting physical laws, a place where the pull of infinite gravity clashes with the push of infinite expulsion. Scientists propose that the Cosmic Anvil could be a similar kind of meeting point, but for dimensions themselves. It might be a zone where a higher dimension is collapsing into a lower one, or where 2 separate dimensional brains, a concept from string theory, are smashing together. The result would be a local breakdown of the rules we depend on. The constants of nature, like the speed of light or the strength of gravity, might fluctuate wildly. Time itself could become twisted or flow in unexpected ways. It's a point where the universe's instruction manual is being rewritten in real time, and we are only just beginning to learn how to read it. This isn't just a new type of object in space, it's a new type of event happening to space. To understand how something as bizarre as a dimensional collapse could even be possible, we need to build a foundation in the physics of dimensions themselves. Our everyday experience is limited to the three spatial dimensions: length, width, and height, plus the dimension of time. These four dimensions form the stage upon which the entire universe plays out. But for nearly a century, physicists have theorized that this stage might actually be much, much bigger, with extra dimensions hidden from our view. The leading framework for this idea is string theory. At its heart, string theory proposes that the fundamental particles of the universe aren't tiny dots but rather unimaginably small, vibrating loops of energy strings. And for the math of these vibrations to work, to produce all the forces and particles we see, these strings must vibrate in not just 3 or 4 dimensions, but in 10 or even 11. Visualizing these extra dimensions is the real challenge. We can't see them or move through them because the theory suggests they are incredibly small, curled up on themselves at a scale billions of times smaller than an atom. A common analogy is to look at a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself down to the size of an ant and walk along its surface, you'd discover a second dimension, a circular dimension curled around the hose's tube. Our universe might be like that hose. We are simply too big to perceive the tiny, curled-up dimensions that are woven into the fabric of spacetime itself. These hidden dimensions aren't empty or inert. Their specific shape and size determine how the strings within them vibrate, which in turn dictates everything from the mass of an electron to the strength of gravity. Now, the stability of these dimensions is absolutely critical to the laws of physics as we know them. For our universe to be predictable and stable, these extra dimensions must be in a steady, unchanging state. But what if they weren't? Theories like the string theory landscape suggest there could be a vast number of possible ways for these dimensions to be configured, each with its own unique physical laws. Most of these configurations would be unstable. This leads us to a terrifying and fascinating possibility, a bubble of true vacuum where the dimensions have settled into a more stable, lower energy state, could begin to form somewhere in the cosmos. This bubble would then expand at the speed of light, rewriting the laws of physics in its wake. Anything caught in this wave would cease to exist as we know it, instantly transformed into something unrecognizable. The Cosmic Anvil could be the epicenter of such an event, a point where this transformative process has begun. It wouldn't be a collision of planets or stars, but a collision of realities, a place where one set of physical laws is actively overwhelming another. The forces at play would be fundamental, operating on the geometry of spacetime itself. It's a concept that stretches our imagination to its limits, suggesting that the universe is not a fixed, eternal entity, but a dynamic and potentially fragile structure, with its deepest foundations subject to change without warning. This journey into the unseen architecture of the universe didn't begin with modern telescopes or supercomputers. Its roots stretch back over a century, to a time when a little-known German mathematician named Theodor Kaluza had a dazzling insight. In 1919, the same year Einstein's theory of general relativity was finally confirmed, Kaluza sent a letter to Einstein himself. In it, he proposed a radical idea. What if we could unify Einstein's description of gravity with James Clerk Maxwell's theory of electromagnetism by simply adding a fifth dimension? Kaluza's math showed that if you wrote Einstein's equations for a 5-dimensional universe, but then assumed that fifth dimension was curled up so small it was invisible, the equations would naturally split. One part beautifully described Einstein's gravity in 4 dimensions, and the extra part perfectly described Maxwell's electromagnetic force. It was as if a new, fundamental piece of the cosmic puzzle had suddenly snapped into place. Einstein was initially captivated, yet deeply skeptical. the idea of an unseen dimension was philosophically jarring, even for the man who had reshaped our concepts of space and time. It took another physicist, Oscar Klein, to refine the idea a few years later. Klein provided a more robust quantum mechanical explanation for why this fifth dimension would be hidden, proposing it was curled into a circle far smaller than an atom. This Kaluza-Klein theory was the first serious scientific framework to suggest that our reality is a projection of a higher dimensional world, a concept that laid the crucial groundwork for everything that followed. For decades, this brilliant yet strange idea remained on the fringes of physics, a tantalizing but unproven possibility. The torch was carried next by a new generation of thinkers in the latter half of the 20th century. The quest to unify all the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces led physicists to develop string theory. This was no minor adjustment. It was a complete overhaul of our picture of reality. The theory replaced point-like particles with tiny, vibrating strings, and it demanded more dimensions to accommodate all the possible vibrational patterns that could represent every known particle and force. First, it required 10 dimensions. Then, in the 1990s, a series of breakthroughs revealed that 5 different versions of string theory were actually just different perspectives of a single, deeper theory operating in 11 dimensions, a framework elegantly dubbed M-theory by physicist Edward Witten. M-theory introduced a truly mind-bending component, brains. These are not the strings themselves, but multidimensional objects upon which strings could end. Our entire universe could be a 3-dimensional brain or 3-brain floating within a higher dimensional bulk. This concept of brains provides a powerful new lens through which to view dimensional interactions. It suggests that the forces we experience, like gravity, might be weak because it is the only force that can freely travel across all dimensions, its strength diluting as it spreads out into the higher dimensional bulk. Other forces, like electromagnetism, are trapped on our brain, which is why they appear so much stronger to us. This brain-world scenario transforms the cosmos from a solitary stage into a potentially crowded multiverse, where other brains with completely different physical laws could be floating mere millimeters away in a higher dimension, forever separate from our own reality. Each step in this theoretical evolution, from Kaluza's 5th dimension to the 11 dimensions of M-theory, has been driven by a handful of visionary physicists building on each other's work. Their contributions have slowly painted a picture of a universe far grander and more hidden than we ever imagined. This historical context is vital because it shows that the concept of the Cosmic Anvil isn't a wild guess. It is the latest, most extreme prediction in a long and respected lineage of scientific thought, a natural consequence of asking what happens when the beautiful, delicate structures proposed by these geniuses are put under the most extreme stress the universe can muster. So how do we search for something as abstract as a collapsing dimension? We can't see it directly, but we can look for its fingerprints, strange, otherwise inexplicable signals etched into the fabric of the cosmos that defy our standard models of physics. Astronomers are now actively hunting for these very anomalies, and a few particularly puzzling observations have emerged as potential signals from a cosmic anvil. One of the most compelling lines of evidence comes from the study of gravitational waves. These are ripples in spacetime itself, first predicted by Einstein and finally detected in 2015. Usually, they are generated by massive, violent events like the collision of black holes or neutron stars, producing a very specific and predictable pattern, a chirp that rises in frequency and amplitude before fading away. But what if we detected a gravitational wave that doesn't play by those rules? Imagine a signal that appears from a region of empty space, with no visible source like a galaxy merger or a supernova to account for it. Even stranger, imagine a gravitational wave that exhibits an bizarre frequency pattern, one that suggests spacetime is being warped not by a massive object, but by a fundamental change in the underlying dimensional geometry of that region. Some researchers speculate that a dimensional collapse could generate a unique, low-frequency hum in the gravitational wave background, a persistent tremor utterly unlike the transient chirps we're used to. Finding such a signal would be like hearing a mysterious, constant drumbeat coming from a supposedly empty room, forcing us to ask what could possibly be causing it. Beyond gravitational waves, another telltale sign could be found in the high-energy radiation that streaks across the universe. Our space telescopes are constantly mapping the sky in gamma rays, X-rays, and other energetic emissions. Normally, the sources of this radiation are well understood: pulsars, quasars, or the remnants of exploded stars. But there are patches of space that emit radiation in patterns that make no conventional sense. For instance, a region might pour out a specific type of cosmic ray with an energy level that is theoretically impossible for any known astrophysical process to generate. Or we might detect a beam of particles that seems to have been focused and amplified by a lens we cannot see, a lens that could be formed by a localized distortion in the fabric of higher dimensions. This would be akin to seeing a spotlight shining in a dark forest with no lamp, no battery, and no explanation for its existence other than a fundamental flaw in the environment itself. Perhaps the most direct evidence comes from meticulous studies of the cosmic microwave background radiation, the ancient afterglow of the Big Bang. This faint echo fills the entire universe and is exquisitely uniform, but not perfectly so. Tiny fluctuations in its temperature tell the story of the early universe's formation. However, some analyses have hinted at something more: large, unexpected cold spots or peculiar alignments in the polarization of this light that are incredibly difficult to explain with our standard cosmology. One provocative theory suggests these anomalies could be scars, the imprint of a pre-Big Bang event, or even a collision with another universe in the multiverse. But another, even more dramatic possibility is that we are seeing the real-time effect of a dimensional instability. A region where dimensions are collapsing could subtly alter the way light and energy travel through it, creating a kind of cosmic shadow or a distortion in the background radiation that appears as a mysterious, inexplicable blotch on our most detailed maps of the primordial universe. Each of these signals on its own is a curiosity, an outlier that scientists work to explain within the existing laws of physics. But when you gather them together, the inexplicable gravitational wave from nowhere, the impossible particle radiation, the anomalous cold spot in the cosmic microwave background, they begin to form a pattern. It's a pattern that points toward a reality that is far more dynamic and volatile than we ever supposed, hinting that in the silent depths between galaxies, the very stage of existence might be cracking under a pressure we are only beginning to perceive. But to truly appreciate the power of these ideas, we need to ground them in a real cosmic mystery, one that has baffled astronomers for decades. A perfect example lies in a strange and powerful force felt across an immense region of space, a phenomenon known as the Great Attractor. Picture our galactic neighborhood, the Milky Way, not as a static island but as a ship adrift on a vast cosmic current. For years, we knew we were moving, but it wasn't until the 1970s that astronomers realized this motion was far too fast and in a strangely specific direction. Something colossal, with a gravitational pull millions of times greater than our own galaxy, was tugging on us and thousands of other galaxies. This invisible, monstrous source of gravity was dubbed the Great Attractor, and it lies in a direction towards the constellation Centaurus, hidden from our direct view by the thick dust and stars of the Milky Way's own galactic plane. The puzzle only deepened with time, even after we managed to peer through the obscuring dust with infrared and radio telescopes, the concentration of visible matter. The galaxies and clusters we could see was simply not enough to account for the tremendous gravitational pull we were experiencing. It was like feeling the powerful, steady tug of a massive underwater current, but looking down to see only a few small streams feeding into it. This discrepancy is a classic signature of dark matter's influence, but the scale and intensity of the Great Attractor led some theorists to wonder if something even more exotic could be at play. What if this wasn't just a clump of dark matter, but a region where the very laws of gravity were being fundamentally altered? This is where the concept of the Cosmic Anvil offers a breathtakingly radical explanation. Imagine if the Great Attractor isn't a thing at all, but a place, a specific point in the cosmos where a local collapse of dimensions is occurring. According to the principles we discussed earlier, such a collapse would create an immense distortion in the fabric of spacetime. One of the most dramatic consequences would be a radical amplification of gravitational forces within that region. The geometry of space itself would be warped, not by a concentration of mass, but by a flaw in the foundational structure of reality. In this scenario, the incredible pull we feel wouldn't be generated by an unseen supermassive object, but by the spacetime equivalent of a massive sinkhole, a vortex of dimensional instability pulling everything in its vicinity toward it. Think of it like a drain in a bathtub. The water flows toward the drain not because the drain is actively sucking it in with some mysterious force, but because the drain creates a low-pressure zone, a distortion in the environment that everything else naturally flows into. A cosmic anvil could be acting as a gravitational drain on a cosmic scale. The galaxies aren't being pulled by a hidden monster in the darkness. They are sliding down a slope in spacetime that has been steepened by a catastrophic event in the very architecture of dimensions. This would explain why we see no single colossal source of light or mass, because the source isn't a collection of objects, but a profound and ongoing event in the framework of the universe itself. It redefines the Great Attractor from a celestial object into a cosmic symptom, a signpost pointing toward a location where reality itself is behaving in a way we are only beginning to comprehend. This idea of a dimensional sinkhole reshaping gravity itself leads us to an even more profound possibility. What if the same fundamental process could explain the two greatest mysteries in all of modern cosmology, dark matter and dark energy? For decades, these two invisible components have been the elephant in the room, making up over 95% of the universe's total content, yet remaining completely undetectable by any conventional means. Dark matter is the mysterious glue holding galaxies together with its gravitational pull, while dark energy is the enigmatic force relentlessly pushing the universe apart, causing its expansion to accelerate. They seem to be opposing forces, one pulling things in and the other pushing them out, and we have no idea what they actually are. The Cosmic Anvil hypothesis offers a stunningly elegant and unified solution. Both phenomena could be different manifestations of the same underlying cause instabilities in the hidden dimensions of reality. Let's start with dark matter. We know it exists because we can see its gravitational effects. Galaxies spin so fast that the visible stars and gas should fly apart, but something with immense gravity holds them together. We just can't see what that something is. Now, imagine if dark matter isn't a particle at all, but a side effect. Think about the force of gravity in our familiar three dimensions. According to some models, if an extra dimension were to begin collapsing or fluctuating, it wouldn't just vanish without a trace. That process would create massive ripples and distortions in the geometry of spacetime around it. These distortions would manifest as an incredibly strong, additional gravitational field in our three-dimensional world. From our perspective, it would look exactly like a huge amount of invisible mass was concentrated there, warping space and pulling on everything nearby. We'd call it dark matter, but it wouldn't be a substance, it would be a symptom. It would be the gravitational shadow cast by a dimensional earthquake happening in a realm we cannot perceive. This would beautifully explain why our decades-long hunt for dark matter particles has come up empty. We're searching for an object when we should be looking for an event. Now consider dark energy. Its effect is the opposite. It's causing the universe to expand at an ever-increasing rate. a discovery that shocked astronomers in the late 1990s. The leading theory is that it's a property of space itself, a constant energy density known as the cosmological constant. But why it has the specific value it does remains one of the biggest puzzles in physics. The Cosmic Anvil framework provides a dynamic alternative. The collapse of a dimension isn't necessarily a quiet event. It could be a tremendously energetic one. As a dimension crumples and transitions to a new state, it might release a colossal amount of potential energy directly into the fabric of spacetime itself. This infusion of energy would act like a constant pressure, pushing the universe apart and accelerating its expansion. In this view, dark energy isn't a static feature of the vacuum but an active, ongoing process, the cosmic fallout from dimensional instability. We are witnessing the universe literally inflating itself from the inside out, powered by the breakdown of its own fundamental architecture. This creates a powerful and startling symmetry. The same underlying phenomenon, dimensional dynamics, could account for both the pull of dark matter and the push of dark energy, simply by appearing in different cosmic contexts. In regions where dimensions are collapsing in a localized way, like within galaxies and clusters, we feel the extra gravitational pull we label as dark matter. On the grandest scales, across the vast emptiness of intergalactic space, the cumulative energy released from countless such events, or perhaps from a universal dimensional evolution, manifests as the repulsive force of dark energy. One single grand mechanism could be behind both of the universe's most dominant and most mysterious features. This isn't just adding a new piece to the puzzle, it's suggesting we've been looking at the puzzle from the wrong angle entirely. The answer to what holds the universe together and what is tearing it apart might not be found by building a bigger particle collider, but by developing a new mathematics to understand the stability or instability of the hidden dimensions that form the true foundation of everything. To truly grasp the significance of these ancient light patterns, we need to understand what the cosmic microwave background, or CMB, actually is. Think of it as the universe's baby picture, taken when it was just 380,000 years old. Before that moment, the cosmos was a searing, opaque plasma, too hot for light to travel freely. As it expanded and cooled, the first atoms formed, and the universe suddenly became transparent. That first flash of light, once a brilliant blaze, has been stretched and cooled by 14 billion years of expansion into a faint microwave whisper that uniformly fills the entire sky. This afterglow is incredibly smooth, but not perfectly so. The tiny fluctuations in its temperature, minuscule variations of mere millionths of a degree, are the seeds from which all cosmic structure grew. Every galaxy, every star, every planet we see today originated from these infinitesimal density variations mapped across the primordial sky. Satellites like Planck have given us an exquisitely detailed map of this radiation, and for the most part, it confirms our standard model of cosmology with spectacular precision. But as with any detailed map, there are a few oddities that stand out, strange features that stubbornly refuse to fit the expected pattern. One of the most famous is the so-called cold spot. This is a large, circular region in the constellation Eridanus that is significantly colder than the surrounding CMB. On its own, a cold patch might not seem unusual, but the size and the statistical significance of this one make it a profound anomaly. It's so large and so cold that the probability of it arising from random chance in our standard model is extremely low, less than 1%. It's like finding a single, perfectly frozen lake in the middle of a vast, temperate continent, a feature that the geological models say shouldn't be there. The conventional explanations for the cold spot have been found wanting. One idea was that it might be a giant cosmic void, an immense region of space with far fewer galaxies and clusters than average. Such a void would act like a hill. Light climbing out of it would lose energy, making the CMB appear colder in that direction. but exhaustive surveys have failed to find a void large enough or empty enough to account for the sheer scale of the temperature drop. The evidence simply isn't there. This leaves scientists searching for more exotic answers, and this is where the concept of the cosmic anvil enters the picture. What if the cold spot isn't a feature imprinted on the CMB, but a shadow cast through it, a shadow from something happening to the fabric of spacetime itself? Imagine a region where dimensions are actively collapsing or interacting. This process would create a profound local distortion in the geometry of the universe. As the ancient light from the CMB traveled across 14 billion years to reach us, it would have passed through this region. The distorted spacetime would act like a lens, but not one that simply magnifies or shrinks. It could subtly alter the energy of the light passing through it, effectively draining a small amount of energy from the photons and leaving that area of the sky appearing colder. From our perspective, it would look exactly like the cold spot. We wouldn't be seeing the collapse itself, but its fingerprint, a lasting chill in the primordial light caused by its journey through a cosmic fault line. But the anomalies don't stop there. The Planck data also revealed peculiar large-scale alignments in the polarization of the CMB. Polarization is the direction in which the light waves oscillate, and it carries information about the very first instance after the Big Bang. The Standard Model predicts that these patterns should be random and evenly distributed across the sky, like a symmetric tapestry. Instead, scientists found strange, large-scale correlations and alignments that seem to defy this randomness. Some have poetically called this the axis of evil, a name that reflects how uncomfortably it challenges our understanding. It's as if the entire universe has a faint, preferred direction, a subtle grain to its structure that shouldn't exist in a perfectly isotropic and homogeneous cosmos. Once again, the interaction of dimensions offers a compelling solution. If our three-dimensional universe is a brain floating in a higher dimensional bulk, it may not be perfectly flat or isolated. It could have a slight tilt or be subject to gentle pressures from neighboring brains. These interactions, happening on a scale far beyond our perception, could impart a subtle preferred direction to the entire structure of our reality. This universal bias would then be imprinted on the very first moments of creation, seeding those large-scale alignments we see in the polarization of the CMB. It wouldn't be an axis of evil, but rather an axis of influence, evidence that our universe is not entirely separate, but is gently brushing up against the architecture of a larger, hidden multiverse. These aren't just quirks in the data, they are potential messages, clues written in the oldest light we can see, pointing toward a cosmos that is far more dynamic and interconnected than we ever dreamed. Now, if dimensions can collapse in the depths of space, could the same process be happening on a more concentrated, violent scale within the most mysterious objects we know? This brings us to one of the most thrilling possibilities in all of theoretical physics, the idea that black holes might not be mere cosmic vacuum cleaners, but something far more profound, potential gateways where dimensions intersect, collapse, or even connect to something else entirely. We're all familiar with the classic image of a black hole, an inescapable prison of gravity from which nothing, not even light, can break free. Its boundary, the event horizon, marks the point of no return. But what if that horizon isn't just a one-way street into oblivion? What if it's a veil, a cosmic curtain that hides a far more complex and bizarre reality from our view? Some physicists speculate that the immense gravitational crush within a black hole could be so extreme that it doesn't just collapse matter. It strains the very fabric of spacetime to its breaking point, potentially causing a localized failure or intersection of dimensions right at the black hole's core, its singularity. Think of a black hole not as a simple hole, but as a knot in the universe's fabric, tied so tightly that the threads of reality begin to fray and unravel. At the center of this knot, the laws of physics as we know them cease to function. General relativity predicts a point of infinite density, but many scientists believe this is merely a sign that our current math is incomplete, that a deeper theory like quantum gravity or string theory must take over. This is where the dimensional gateway idea truly ignites. According to some interpretations of string theory, the singularity might not be a point, but a highly energetic, vibrating tangle of strings and membranes. This frenzy of activity could be constantly probing and stressing the boundaries between dimensions, perhaps even punching a microscopic hole into the higher dimensional bulk that M-theory proposes. In this view, the event horizon acts as a perfect cloak for this dimensional breach. It's a region of such extreme time dilation and spatial warping that any signal or information about what's happening inside is utterly trapped, forever hidden from our universe. From our perspective outside, the black hole appears simple: mass, spin, and charge. But inside, the reality could be unimaginably complex. Matter and energy falling through the horizon might not be crushed into nothingness. Instead, it could be transformed, its information encoded onto the horizon's surface, a concept known as the holographic principle before being funneled through a dimensional shortcut. It might be rerouted, its fundamental properties translated as it passes into another dimensional realm. This leads to the most famous yet controversial implication, the idea of an Einstein-Rosen bridge or a wormhole. If a black hole does represent a point of dimensional intersection, it could, in theory, connect to a corresponding point of expulsion, a white hole in another part of our universe, or even in a completely different universe altogether. The matter falling into one could, in this spectacularly speculative scenario, be violently ejected out the other. Of course, this remains firmly in the realm of theory. The immense tidal forces and instability of such a passage would likely shred any object or information to its most fundamental parts long before it could complete the journey intact. Yet, the mathematics allows for the possibility, painting a picture of black holes not as in points, but as potential transit hubs in a cosmos of hidden dimensions, where the fabric of reality is woven with threads that can, under the most extreme conditions, loop back on themselves or tie into entirely new patterns. This brings us to the ultimate theoretical counterpart to the black hole's destructive crush, the white hole. If a black hole is a cosmic drain from which nothing can escape, a white hole is its impossible opposite, a cosmic fountain from which matter and energy perpetually erupt and into which nothing can ever enter. It's a one-way street in reverse, a point in space where the universe is constantly pouring its contents outward, defying the relentless pull of gravity that governs everything else. While no white hole has ever been observed, they are a mathematically valid, if exotic, solution to the equations of general relativity. They represent the ultimate expression of cosmic expulsion, and in the context of dimensional collapse, they offer a breathtakingly elegant potential outlet. If a black hole is where a dimension is collapsing inward, a white hole could be the corresponding point where that same energy and information is being violently expelled back into our reality from another dimensional realm. Imagine the process not as a simple destruction, but as a transformation. Matter and energy falling into a black hole, compressed beyond all recognition at the singularity, might not be annihilated. Instead, the extreme conditions could be acting as a cosmic converter, translating that matter into a form that can travel along a hidden dimensional pathway. The black hole singularity, under this model, wouldn't be a final destination but a transfer station. The converted energy would then travel through this higher dimensional shortcut, perhaps a wormhole stabilized by the very strings and brains of the theory, only to be violently reborn out of a white hole somewhere else in the cosmos. This white hole wouldn't be a quiet event. It would be a titanic explosion of energy and newly formed particles, a genesis event that could appear to us as a mysterious, short-lived quasar or a source of inexplicably high energy radiation with no visible cause. The energy signature of such an event would be unlike anything we know. Instead of the predictable emissions from a pulsar or the aftermath of a supernova, a white hole eruption would likely involve particles and radiation with bizarre, unexpected properties. We might detect a jet of particles moving at fractions of the speed of light, but with an energy spectrum that doesn't match any known astrophysical process. Or we could witness the sudden, spontaneous appearance of matter from a seemingly empty point in space, as if the universe itself had a tiny, invisible tear that was briefly leaking reality from another place. Finding such an anomaly would be the smoking gun, the evidence that our universe is not a closed system, but is intricately connected to a larger, multidimensional framework. This idea of a black hole-white hole system creates a stunning new perspective on the life cycle of matter and energy. It suggests that what we perceive as the end, a star collapsing into a black hole, might actually be a beginning in a different part of the cosmos. Our universe could be woven through with these invisible tunnels and fountains, a vast, interconnected network where the end of one story is merely the opening chapter of another, playing out across dimensions we are only now learning to imagine. It transforms the cosmos from a collection of isolated objects into a dynamic, breathing entity, constantly recycling itself through gateways hidden in plain sight. To truly appreciate the idea of dimensions collapsing, we must venture into the most counterintuitive and bizarre realm of physics, the quantum world. Here, at scales so small they defy imagination, the smooth, predictable fabric of spacetime we take for granted dissolves into a seething, chaotic frenzy. This is the domain of quantum foam, a concept that suggests the very foundation of reality is anything but solid and stable. Imagine zooming in on the universe past atoms, past protons and neutrons, down to the Planck length, a scale so tiny that 1,000,000 trillion of them would fit across a single atom. At this unimaginable resolution, the calm geometry of Einstein's spacetime doesn't just get bumpy, it becomes a turbulent, frothing sea. Empty space isn't empty at all. It is a constantly boiling cauldron of virtual particles spontaneously flashing into and out of existence, borrowing energy from the vacuum for fleeting moments before vanishing again. This isn't just empty space behaving strangely. This is the nature of reality itself at its most fundamental level. This ceaseless activity means that the fabric of spacetime is not a static stage. It is a dynamic, living thing constantly fluctuating. For an unimaginably brief instant, a tiny region of space might warp into a minuscule loop or a tunnel. The energy density might spike and the curvature of spacetime might become extreme. In these fleeting moments, the conditions could be just right for something extraordinary to occur. The delicate, curled-up dimensions that string theory proposes, usually stable and unchanging, could be jostled and jolted by this quantum turbulence. A fluctuation with enough energy could momentarily cause these tiny dimensions to pinch, to unravel, or to merge with one another. It would be a microscopic dimensional earthquake, a brief collapse or reconfiguration happening over a scale and time so small we could never directly observe it. Think of it like the surface of a carbonated drink with bubbles constantly forming and popping. Each pop is a tiny event. Now, imagine if each of those pops wasn't just a release of gas, but a temporary rewiring of the very laws of physics in that pinpoint location. The implications of this are staggering. It suggests that the stability of our universe is not absolute but statistical. The laws of physics we depend on are not ironclad rules engraved on cosmic stone. They are the average, large-scale outcome of quintillions of these random quantum events happening every second in every cubic centimeter of so-called empty space. Most of the time, these fluctuations cancel each other out, and we experience a calm, predictable reality. But what if one didn't cancel out? What if, by the sheer random chance of quantum statistics, a particularly large and energetic fluctuation occurred? In a universe governed by probability, even events with astronomically low odds can, given enough time and space, eventually happen. A fluctuation powerful enough could, in theory, trigger a more significant and lasting collapse, a tiny bubble of true vacuum where the dimensional architecture settles into a new, lower energy state. This bubble wouldn't just pop like the others. It could expand at the speed of light, its new laws of physics overwriting the old ones in an unstoppable wave. The Cosmic Anvil, then, might not be a singular, static location, but the epicenter of such a rare and catastrophic quantum event, a place where a random fluctuation in the foam grew instead of subsided, forever changing the cosmos around it. This brings us to one of the most fascinating and mind-bending theoretical constructs that could physically forge a cosmic anvil, the cosmic string. To understand what these are, we need to shift our perspective from the quantum foam to the grandest scales of the universe, all the way back to its very first moments. In the instant after the Big Bang, as the fiery, nascent universe expanded and cooled, it underwent a series of profound phase transitions, much like water freezing into ice. And just as freezing water can trap air bubbles or form cracks, these cosmic phase transitions could have trapped immense flaws in the very structure of spacetime itself. A cosmic string is one such flaw, not a string made of atoms or particles, but a truly fundamental defect, an infinitely long, unimaginably thin scar in the fabric of reality, a one-dimensional crack in the universe that has been there since the beginning of time. The predicted properties of these objects are so extreme they defy belief. A cosmic string would be narrower than a proton, yet a single inch of it could weigh as much as a mountain range. This incredible mass is pure energy, the energy stored in the strained, twisted geometry of the spacetime that forms the string's core. It would possess immense tension, so great that it would literally whip through the universe a Chinese letter, the speed of light. And because it is a flaw in spacetime itself, its gravitational influence is unlike anything else. It wouldn't just pull objects toward it, it would warp space in a way that creates a unique kind of lens. A galaxy on the other side of a cosmic string would appear to us not as one image, but as two identical, mirrored images side by side in the sky, a perfect cosmic double. This is because the string slices through space, creating a deficit in the angle around it. A pie slice of reality is missing. Light traveling past the string on either side is bent toward the gap, forcing it to take two different paths to our eyes. But the most dramatic, most dangerous property of a cosmic string emerges not from a single string, but from what happens when two of them cross paths. Picture two of these infinitesimally thin, ultra-dense scars slicing through the void. As they approach one another, the spacetime around them becomes increasingly strained, warped by their incredible mass and tension. If they were to simply pass through each other, the event would be violent, sending powerful gravitational ripples across the cosmos. However, some theories suggest a far more spectacular and terrifying possibility. They could become entangled. The two strings could tie themselves into a knot of pure spacetime defect. At the point of that intersection, the strain on the fabric of reality would be beyond anything the universe has experienced since its first second of existence. The energy density, the sheer gravitational pressure at that microscopic point, would be absolutely off the scale. It is at this precise, unimaginable point of contact that a cosmic string intersection could become the trigger for a dimensional collapse. The forces at play would be so extreme that they could overwhelm the stabilizing mechanisms that keep the tiny, curled-up dimensions of string theory in their settled state. Think of it like pressing the tip of a needle onto a balloon. The balloon's surface can handle pressure evenly distributed, but focus all that force onto a single, infinitesimal point and it pops. In this case, the pop wouldn't be a sound but a fundamental restructuring. The intersecting cosmic strings could act as that cosmic needle, their focused energy piercing through the fabric of our familiar four-dimensional spacetime and into the realm of the higher dimensions. This could initiate a local collapse, a chain reaction where the extra dimensions unravel or reconfigure into a new, lower energy state. the intersection point would become the anvil, the forge where a new set of physical laws is hammered into existence, a singularity of change that then expands outward at the speed of light, rewriting reality in its wake. It's a hypothetical event of almost biblical power, where the oldest scars in the universe could become the catalysts for its most profound transformation. This concept of a cosmic string intersection acting as a catalyst for a dimensional collapse is a staggering one, but it leads us to an even grander possibility. What if the cosmic anvil isn't just a random, isolated event within our universe, but a point of contact with an entirely different one? To explore this, we need to venture into the realm of the multiverse, a theory that suggests our cosmos might be just one bubble in a vast, frothing sea of realities. And one of the most compelling frameworks for this idea comes directly from the same branch of physics that gave us extra dimensions, string theory and its extension, M-theory. Within M-theory exists a fascinating concept called the brain-world scenario. The word brain is short for membrane, and it generalizes the idea of a dimension. A zero brain is a point, a one brain is a string, a two brain is a sheet, and so on. Crucially, this theory proposes that our entire universe with its three spatial dimensions might actually be a three-brain, a vast, flat membrane floating within a higher dimensional space called the bulk. This isn't just a poetic metaphor, it's a serious mathematical model that helps solve several deep problems in physics. For instance, it could explain why gravity is so weak compared to the other fundamental forces. The idea is that while forces like electromagnetism are trapped on our brain, gravity can leak out into the bulk, diluting its strength from our perspective. Now, if our universe is a three-brain drifting in this higher dimensional void, what's to say it's the only one? The bulk could be populated by countless other brains, each one its own separate universe, each with its own unique set of physical laws and constants. Some might be almost identical to ours with slight variations. A universe where gravity is slightly stronger or where the electron has a different charge. Others could be unimaginably alien, governed by physics so different that matter as we know it could never form. These parallel universes would typically be forever separate, isolated islands in the vast bulk, unaware of each other's existence. But what happens if these brains, while floating through the bulk, happen to collide? The sheer scale of such an event is difficult to overstate. It wouldn't be two planets smashing together. It would be two entire universes, two entire sets of physical reality, making contact across a higher dimension. The energy released at the boundary of that collision would be beyond astronomical. From the perspective of beings living on one of those brains, it would appear not as a physical object hitting another, but as a cataclysm emerging from the very fabric of space itself. An immense wall of energy and force would sweep across the cosmos, fundamentally altering everything in its path. This is where we find a profound and elegant connection to the cosmic anvil. A collision between two brains could manifest within one of those universes exactly as a localized dimensional collapse. The point of contact, the epicenter of the collision, would be a region of indescribable energy and instability. The laws of physics would be in chaos as the fundamental rules of two separate realities vied for dominance. The immense forces could cause the compactified dimensions within that region to violently uncurl or recollapse into a new, stable configuration. The gravitational anomalies, the strange radiation, the inexplicable cold spot in the CMB, all the potential signals we discussed earlier could be the cosmic aftershocks of such a monumental impact. The Great Attractor's impossible pull might not be a sinkhole within our universe, but the lingering gravitational wake of a nearby brain passing close by in the bulk, its presence warping our local spacetime. This idea transforms the cosmic anvil from a terrifying anomaly into a potential window. It could be a scar, a permanent reminder that our universe is not alone. It might be evidence that the silent, empty space between galaxies is not empty at all, but is in fact the stage for events of a scale and grandeur we are only beginning to comprehend. A dimensional collapse might be the closest we can ever come to directly observing our multiverse neighbors, not by seeing them, but by feeling the reverberations of their passage through the higher dimensional cosmos we all call home. If the fabric of spacetime is buckling under the strain of dimensional collapse, one of the most bizarre consequences we could witness involves time itself. We already know from Einstein's theory of relativity that time is not a universal constant. It's a flexible dimension that can be stretched and warped by gravity and velocity. A clock on a satellite in orbit ticks measurably faster than one on the Earth's surface. Now amplify that effect by orders of magnitude. A region undergoing a dimensional collapse would represent a cataclysmic distortion of local spacetime geometry, creating a gravitational field so intense that it would twist the flow of time in ways that defy our everyday intuition. Consider a simple thought experiment. Imagine two identical, incredibly durable clocks. We place one clock here on Earth, and we send the other on a mission toward the suspected location of a cosmic anvil. As the spacecraft approaches this region of collapsing dimensions, the gravitational pull, or rather the spacetime distortion, would become unimaginably strong. From our perspective, safely back on Earth, we would watch the signals from that spacecraft's clock slow down. First, the seconds would tick by just a hair slower than ours. Then the delay would become a crawl. For every hour that passes for us, only a few minutes might pass for the clock on the ship. If it could reach the very epicenter of the collapse, time might appear from our outside viewpoint to grind to a complete halt. The clock would seem frozen, yet from the perspective of anyone or anything on that ship, their time would feel perfectly normal. They would have no idea that centuries were flashing by in the universe outside their bubble of distorted reality. This isn't just a dramatic scenario, it's a direct prediction of general relativity applied to an extreme environment. The equations tell us that where gravity is strongest, time flows slowest. A dimensional collapse would create a gravity well so deep it would make a black hole look like a gentle valley. The closer you get to that point, the more you are climbing a steep temporal hill. This leads to a profound and unsettling possibility. These regions might not just be dangerous because of their immense forces, they could be traps from which there is no return to your own time. A spacecraft that ventured too close might, from its crew's perspective, reverse course after only a few hours of study. But when they returned to Earth, they could find that thousands of years had passed. They would become permanent exiles from their own era, victims of a one-way trip into the future. The effects could also work in reverse under certain theoretical models. If the collapse is creating a kind of repulsive gravity or a white hole-like expulsion of energy, it could theoretically create a region where time flows faster than the surrounding universe. An observer watching from a distance might see a flash of intense activity, with stars seeming to form, live, and die in the blink of an eye, while anything inside that bubble would perceive the external universe as being stuck in slow motion. These temporal distortions would leave clear, if bizarre, observational evidence. We might detect a galaxy where stellar evolution appears to be radically accelerated, with stars burning out impossibly fast. Or we might find a quasar that flickers with a rhythm that suggests its light is being stretched and compressed by a fluctuating time field on its journey to us, a clear sign that something is terribly wrong with the flow of time in that part of the cosmos. The hunt for these elusive cosmic signatures brings us to some of the most sensitive instruments ever built by humanity, the gravitational wave observatories known as LIGO and Virgo. These facilities are essentially giant, L-shaped ears tuned to the vibrations of spacetime itself. For years, their primary mission has been to listen for the telltale chirps created by the collisions of black holes and neutron stars, and they have done so with spectacular success, opening an entirely new window onto the universe. But buried within the mountains of data they collect could be something even more extraordinary. Signals that don't fit the established patterns, whispers from events that defy our current understanding of physics. Most gravitational wave signals follow a very predictable pattern. When two massive objects spiral inward toward a cataclysmic merger, they create ripples that increase in both frequency and amplitude, producing a characteristic rising tone that ends abruptly in a final ring-down as the new, single object settles into its stable form. It's a clean, mathematically beautiful signature that aligns perfectly with Einstein's predictions. However, the data streams from LIGO and Virgo have also contained a handful of anomaly signals that are far messier, more complex, and utterly perplexing. Some events appear to originate from regions of seemingly empty space, with no optical or electromagnetic counterpart found by telescopes scanning the same area of the sky. It's like hearing a tremendous crash from an empty room. The sound is undeniable, but the source is completely invisible. One of the most intriguing possibilities is that these anomalous signals are not coming from the collision of objects within our three-dimensional universe, but from a violent event happening to the dimensions themselves. Imagine the fabric of a higher dimension beginning to fray or collapse. This wouldn't be a smooth process. It would be a tumultuous, chaotic rupture, sending powerful shockwaves rippling through the bulk of higher dimensional space. As these shockwaves travel, they would interact with our three-dimensional brain, transferring energy and creating a unique kind of tremor in our local spacetime. The gravitational wave signal from such an event wouldn't sound like a clean chirp. Instead, it might manifest as a sustained, low-frequency hum, a burst of incoherent noise, or a signal with bizarre overtones and harmonics that don't correspond to any known type of celestial object. Scientists are now developing sophisticated new algorithms to sift through the observatory data, specifically searching for these statistical outliers. They are looking for signals that have the right feel of a dimensional event, perhaps a waveform that suggests spacetime was being stretched and compressed in multiple directions simultaneously, a signature that could only be produced by forces acting from outside our familiar three dimensions. Finding such a signal would be a monumental breakthrough, not just confirming the existence of extra dimensions, but providing our first direct evidence that they are dynamic and can interact with our reality in tangible, detectable ways. It would transform our understanding of the cosmos from a collection of objects within space to an appreciation of space itself as an active, evolving participant in the drama of the universe. Mathematical models give us the only real window into the behavior of a cosmic anvil, translating this mind-bending concept into a language the universe itself understands: equations. While we can't film a dimension collapsing, theorists can build intricate frameworks that predict exactly how such an event would ripple through our observable reality. These models primarily draw from two powerful but often conflicting pillars of physics: Einstein's general relativity, which governs the very large, and quantum field theory, which governs the very small. A dimensional collapse is the rare event that forces these two worlds to collide in a physicist's calculations. From the perspective of general relativity, the key player is the Einstein field equations. These are the elegant, deceptively simple formulas that describe how matter and energy tell spacetime how to curve, and how that curved spacetime, in turn, tells matter and energy how to move. Normally, we solve these equations for a stable, four-dimensional universe, but to model a dimensional collapse, physicists modify them to include extra dimensions. They might start with a metric tensor, a mathematical object that defines the distance between every point in spacetime, that is designed to change over time. Imagine this tensor as a complex, multi-layered grid that maps the entire universe. In a stable state, all the grid lines are straight and evenly spaced. But in a collapse model, the grid lines representing one of the compact, curled-up dimensions would begin to shrink, pinching closer and closer together. The equations then calculate how this violent pinching in the hidden dimensions warps the grid lines of our familiar four-dimensional spacetime, creating immense, phantom-like gravitational fields and exotic energy distributions that would have no other possible source. On the quantum side, physicists turn to the tools of quantum field theory. Here, the vacuum of space is not empty, it's a seething soup of quantum fields. Each fundamental particle is just a localized vibration in its respective field. The stability of these fields, and thus the stability of particles themselves, depends critically on the number of dimensions they exist in. A model for dimensional collapse would describe the universe using a higher dimensional quantum field theory. As one of those dimensions collapses, the so-called vacuum expectation value of these fields would be forced to change abruptly. This is a bit like suddenly changing the fundamental tension on a vast, invisible network of rubber sheets. The entire system would be thrown into chaos. The equations predict that this would release a colossal burst of energy and generate a shower of new, potentially exotic particles as the fields desperately try to settle into a new, stable state consistent with the new, lower-dimensional reality. The real challenge and the most active area of research is finding a way to unify these two descriptions into a single theory of quantum gravity. String theory and its extension, M-theory, are the leading candidates here. They naturally incorporate extra dimensions from the start. In these frameworks, a dimensional collapse isn't just about geometry changing. It's about the entire landscape of possible universes shifting. The math involves calculating the transition of the universe from one vacuum state to another, from a valley in the cosmic landscape to a deeper, more stable one. This process is described by equations for instantons and bubble nucleation, which calculate the probability and the dynamics of a tiny bubble of the new reality spontaneously forming and then expanding at the speed of light. The equations predict the precise thickness of the wall of this expanding bubble and the incredible energy density difference between the old universe inside and the new universe outside. To visualize these abstract equations, imagine a simple graph. On one axis, you have the size of the extra dimension. On the other, you have energy. The graph would show a hill and two valleys. Our current universe sits happily in one valley, a stable low-energy state. The other valley represents a universe with a different number of stable dimensions, perhaps even a true vacuum. The mathematical models calculate the energy required to roll our universe over that hill and into the new valley. The resulting graphical representation wouldn't be a gentle slope, it would be a precipitous cliff, a sheer drop in energy that signifies a catastrophic, irreversible change in the very rules of existence. These models, while highly theoretical, are our best guess at the blueprint for reality's most extreme makeover, providing the mathematical fingerprints we so desperately need to search for in the cosmos. The sheer scale of these cosmic possibilities is staggering, but to truly grasp their significance, we have to bring them home. What would it mean for us here on Earth if a dimensional collapse event began not in some distant galaxy, but in our own cosmic backyard? The implications are so profound they border on the apocalyptic, transforming a thrilling theoretical concept into a deeply personal and terrifying thought experiment. First and foremost, the very laws of physics as we know them would cease to apply. This isn't just a change in weather, it's a change in the fundamental rules that govern existence. The constants that underpin our reality, the speed of light, the strength of gravity, the charge of an electron are the foundation upon which everything is built. If a wave of dimensional collapse were sweeping through our solar system, these constants would begin to fluctuate wildly. The precise nuclear forces that hold atoms together would destabilize. Matter itself would simply unravel. A tree wouldn't combust or freeze. It would disintegrate into a cloud of fundamental particles as the atomic bonds that gave it structure instantly vanished. The ground beneath our feet would lose its solidity, and the air we breathe would cease to be a stable gas. our bodies, complex structures built on eons of stable physics, would simply come undone in an instant, not with a bang, but with a silent, fundamental dissolution into chaos. Beyond the disintegration of matter, the flow of causality would break down. Our entire understanding of cause and effect is predicated on a stable arrow of time. In a region of collapsing dimensions, time could become scrambled. You might witness events happening in reverse or experience moments of your future before your past. The very concept of a continuous consciousness would be impossible in an environment where time loops, fractures, or stops altogether. Communication would be meaningless if every word spoken could be instantly erased by a shift in the local timeline. It would be a reality not just of physical chaos, but of existential absurdity where nothing could be predicted, remembered, or reliably experienced. Perhaps most frightening is the silent and invisible nature of such an event. There would be no warning siren for the end of physics. The wave of collapse would likely travel at the speed of light. We would have zero advance notice. One moment, the universe would be normal. The very next picosecond, the new laws would be upon us. Our most powerful telescopes would be useless because the light showing us the approaching wave would be traveling at the same speed as the wave itself. We would literally see our demise in the same instant we experienced it. It is the ultimate cosmic ambush, a rewrite of reality so total that there is no surviving it, only being replaced by whatever new, alien physics emerges from the other side. This terrifying scenario is, of course, wildly speculative. The probability of such an event occurring anywhere in the universe, let alone nearby, is astronomically low based on our current understanding. But that's precisely why it's such a powerful concept. It forces us to confront the breathtaking fragility of our existence. We are not just living on a planet orbiting a star. We are inhabiting a very specific and potentially very rare stable valley in a vast cosmic landscape of possible physical laws. Contemplating the cosmic anvil isn't about fostering fear, but about inspiring a profound appreciation for the delicate and extraordinary balance that allows us and our universe to exist at all. It reminds us that the greatest mysteries are not just out there among the stars, but are woven into the very fabric of our being. So how do we go from these incredible theories to actually finding proof? The hunt for a cosmic anvil is on, and it's driving the design of some of the most ambitious scientific instruments ever conceived. This isn't about building a bigger telescope to simply see farther. It's about inventing entirely new ways to perceive the universe, to sense the invisible architecture of reality itself. The strategy is multi-pronged, combining the immense with the infinitesimal, scanning the vastness of space while also probing the deepest fabric of matter. In space, the next generation of observatories is being designed with these exotic phenomena in mind. The European Space Agency's planned Laser Interferometer Space Antenna, or LISA, will be a revolutionary gravitational wave observatory not constrained by Earth seismic noise. Imagine 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, connected by lasers. This giant, orbiting ear will be exquisitely sensitive to the low-frequency hum of the universe, the very range where a sustained, anomalous rumble from a dimensional collapse might be detected. Unlike LIGO, which hears the brief chirps of black hole mergers, LISA could listen for the continuous drone of a cosmic fault line grinding away over eons. Alongside it, advanced telescopes like the James Webb successors will be tasked with performing deep field surveys, not just to find ancient galaxies, but to meticulously map the cosmic microwave background with even greater precision, hunting for new and even more bizarre anomalies that could be the scars of dimensional interactions. On the ground, the quest continues within immense particle colliders. While the Large Hadron Collider was built to find particles like the Higgs boson, analyzing its data can also look for the unexpected signatures of extra dimensions. One tantalizing prediction is that if extra dimensions are real and accessible at high energies, colliders might produce particles that seem to simply disappear, carrying energy away into a hidden dimension. It would be the ultimate magic trick, energy vanishing without a trace, not because of an error in the detector, but because it literally exited our dimensional plane. Future colliders with energies far beyond the LHC could be explicitly designed to create these micro black holes or probe the stringy nature of reality, potentially creating a miniature, controlled dimensional fluctuation right here on Earth, offering us a fleeting glimpse into the mechanics of the multiverse. Perhaps the most futuristic proposals involve sending probes directly into the fray. Concepts for interstellar missions like breakthrough starshots aim to send tiny, laser-propelled sails to Alpha Centauri could one day be retargeted. Instead of heading for the closest star, a probe could be sent on a centuries-long journey toward a suspected anomaly like the Great Attractor. While we wouldn't live to see the data, such a mission would be humanity's ultimate test of a hypothesis, a message in a bottle sent to the edge of a cosmic mystery. These probes would be equipped with sensors far beyond our current imagination, designed not just to map planets, but to measure the local constants of nature, checking if the speed of light or the strength of gravity is different the closer they get to the epicenter, providing the first in situ confirmation that the laws of physics are not universal but local. This multi-front search from the quantum to the cosmic represents our species' determined effort to move from wondering about the universe's deepest secrets to actively uncovering them. Of course, the scientific community is built on a foundation of healthy skepticism, and a discovery as profound as a collapsing dimension demands that we rigorously challenge the evidence. Before we can fully embrace such a revolutionary idea, we must first rule out all the more mundane possibilities. Could the anomalies we've attributed to a cosmic anvil simply be the result of something far less exotic? The answer is a definitive yes, and exploring these alternative explanations is not a dismissal of the idea, but a necessary step in the scientific process. One of the most common and critical sources of error in any observation is the instrument itself. Our telescopes, gravity wave detectors, and satellites are marvels of engineering, but they are not infallible. The signals we hunt for are often incredibly faint, buried deep within a sea of background noise. A subtle instrumental glitch, a misaligned mirror, or even a software bug in the complex algorithms that process raw data could potentially generate a false signal that looks, for all intents and purposes, like a profound cosmic mystery. The cold spot in the cosmic microwave background, for instance, could theoretically be an artifact of the way the Planck satellite data was processed and cleaned to remove the foreground glow of our own galaxy. Scientists spend countless hours modeling and subtracting these known sources of interference, but an imperfect model could leave behind a ghost in the machine, a residual anomaly that we then misinterpret as a feature of the primordial universe. Before we point to a collapse of dimensions, we must be absolutely certain we are not simply seeing the digital equivalent of a smudge on the lens. Beyond our own technology, the universe itself is filled with astrophysical processes we are still struggling to understand. The catalogue of known celestial objects and events is vast, but it is not complete. The inexplicable gravitational wave signal with no visible source might not be from a dimensional rupture, but from a previously unknown class of black holes. Perhaps ancient primordials from the dawn of time, or a quiet merger of objects so dark they emit no light we can detect. The strange high-energy radiation could be the signature of a hyper-advanced type of pulsar or magnetar, a stellar corpse with magnetic fields so intense they warp physics in ways we haven't yet modeled. The Great Attractor's pull might not be a dimensional sinkhole, but an immense concentration of cold, dark matter in a configuration our simulations haven't predicted. The history of astronomy is filled with moments where a mysterious signal was later explained by a new type of star, a novel galactic structure, or a fresh understanding of a known process. Invoking new physics is the last resort, not the first. Perhaps the most compelling alternative lies in the realm of gravity itself. Einstein's theory of general relativity has passed every test thrown at it for over a century, but it has never been probed at the immense scales of galaxy clusters and the cosmic web. It is entirely possible that we do not need extra dimensions or collapsing realities to explain these gravitational anomalies. Instead, we might simply need a modified theory of gravity, a tweak to Einstein's equations that accounts for the observed effects without the need for invisible dark matter or exotic dimensional phenomena. Theories like modified Newtonian dynamics, propose that gravity behaves differently at extremely low accelerations, such as those found in the outer reaches of galaxies. While MOND has its own set of challenges and has struggled to explain all the observations, it represents a more conservative approach than rewriting the dimensional fabric of the cosmos. It suggests that the problem isn't with the universe, but with our current understanding of one of its most fundamental forces. This rigorous process of doubt and elimination is what gives science its strength. Every proposed alternative, from a software bug to a new law of gravity, forces the proponents of the Cosmic Anvil hypothesis to sharpen their models and predictions. They must demonstrate that their idea is not just possible, but that it is the best explanation, the one that accounts for all the data where others fall short. This back and forth is not a weakness, it is the engine of discovery. It ensures that when we finally do point to a region of space and declare that dimensions are collapsing there, we can do so with a confidence born not from excitement, but from having eliminated every other possibility. The truth is often found not in the first exciting idea, but in the last one standing after a brutal and honest competition. These concepts reach far beyond the equations on a whiteboard, spilling over into the stories we tell and the fundamental questions we ask about our own existence. The idea that reality's foundations might be unstable has become a powerful engine for science fiction, providing a new language for our oldest fears and curiosities. For decades, tales of alien invasions or asteroid impacts have represented external threats, but the notion of a dimensional collapse presents a far more intimate and profound danger, a threat not to our world, but to the very rules that make a world possible. It's the difference between a house catching fire and the laws of thermodynamics suddenly ceasing to exist. One is a disaster within reality, the other is a disaster to reality. This shift is vividly clear in modern storytelling. Films and novels now grapple with realities that are fundamentally broken or glitching. A crack in spacetime isn't just a plot device, it's a central metaphor for existential uncertainty. Characters aren't just fighting to save their lives, but to preserve a coherent reality where cause and effect still have meaning. These narratives resonate because they tap into a deep-seated anxiety that our comfortable, predictable world is a fragile illusion, and that beneath the surface lies a chaos we can scarcely comprehend. Science fiction has always held a mirror to our hopes and fears, and the reflection we see now is one of a generation confronting the possibility that the universe itself might be transient and unstable. This cultural conversation naturally bleeds into the realm of philosophy, reigniting ancient debates with startling new urgency. If dimensions can collapse and physical laws can change, what does that say about the nature of reality itself? For centuries, philosophers have pondered whether mathematical truths are discovered or invented. Do we find the laws of physics or do we create them? The Cosmic Anvil hypothesis tilts the scales dramatically toward discovery. It suggests a vast and possibly infinite landscape of potential physical laws, a cosmic catalogue of possible realities. Our universe, with its specific constants that allow for galaxies, planets, and life, might not be a deliberate creation, but a single, fortunate roll of the dice. We aren't living in a universe designed for us. We are living in a universe that, by sheer chance, allows us to be. This perspective, known as the anthropic principle, is both humbling and empowering. It diminishes any notion of a central, privileged position for humanity in the cosmos. We are not the purpose of the universe, we are a fleeting byproduct of its otherwise random parameters. Yet, it also places an incredible weight on our shoulders. If our reality is just one possibility in a multiverse of alternatives, then the values and constants we measure are not universal truths, they are local ordinances. This forces us to ask what, if anything, is truly fundamental. Is consciousness a mere accident of bio-friendly physics, or does it point to something deeper that might persist even if the dimensional fabric changes? The collapse of dimensions doesn't just challenge our physics, it challenges our very understanding of what is real and what is necessary. Ultimately, these ideas filter down to a deeply personal level, influencing how we view our own place in the grand scheme of things. The vast, impersonal forces of the cosmos have always evoked feelings of awe and insignificance, but the potential for dimensional instability adds a new layer of fragility to that awe. Our lives, our history, and our entire civilization are not just tiny in space and time, but are dependent on a specific and potentially precarious architectural setup of the universe. This can be a terrifying thought, but it can also be a source of profound meaning. It suggests that our existence, however brief and localized, is an incredible statistical improbability. The fact that we are here at all, in a universe that permits our form of life, is a wonder worth contemplating. It invites a sense of cosmic gratitude, a recognition that every moment of experience is a gift made possible by a staggeringly unlikely alignment of physical laws, an alignment that, somewhere in the darkness between the stars, might already be coming undone. To help us really unpack what all of this could mean, I'm joined by a leading theoretical cosmologist, someone who spends her days thinking about these very possibilities. Doctor, thank you for being here. For our viewers who are just wrapping their heads around this, can you give us your simplest explanation of what the Cosmic Anvil might actually be? Of course, and please call me Alara. Think of our universe not as a static, unchanging stage, but as a living, breathing thing. It has a structure, a framework. Now, that framework is built from the dimensions we experience: length, width, height, and time, but we have very good theoretical reasons to believe there are more tiny dimensions curled up so small we can't perceive them. The Cosmic Anvil is the name we've given to a hypothetical point where that framework is under such immense stress that it's beginning to fail. It's not a thing you could hit with a spaceship. It's more like a storm in the fabric of reality itself, a place where the rules are being rewritten. And what could cause such a catastrophic failure of physics itself? That's the million-dollar question, isn't it? The leading theory points to something called a phase transition. We see these all the time in everyday life. Liquid water is stable, but when it gets cold enough, it undergoes a phase transition and becomes ice. The structure changes. Now apply that to the vacuum of space itself. Our universe might be in a metastable state, seemingly stable, but actually like a ball sitting in a small valley on the side of a much larger mountain. It's comfortable there, but if it gets a big enough push, it could roll down into a much deeper valley, a true vacuum. That push could be a random, massive quantum fluctuation, or something more dramatic like the intersection of cosmic strings. The moment that transition begins at a single point, that point becomes the anvil. The new, stable state of the universe, with its new laws of physics, begins to expand outward from that point at the speed of light. That's a terrifying thought. If such an event began, would there be any warning at all? Almost certainly not in the way we'd hope. The wave of change would propagate at light speed. The first sign of it would be the change itself arriving. There would be no signal that could outrun it to warn us. One moment, the physics that allows our atoms to hold together, that allows time to flow forward, would be in place. The next moment, it would be replaced by a new set of rules. From our perspective, it would be instantaneous and total. It's the most absolute form of change imaginable because it doesn't just destroy everything, it redefines what everything is. Given how dire that sounds, should this be something we're actually worried about? From a practical, everyday perspective, absolutely not. The probability of such an event occurring in our observable universe, let alone near us, is so infinitesimally small that it's not a legitimate concern. It's like worrying that all the air molecules in the room will spontaneously congregate in one corner and suffocate us. The math allows for it, but you'd be waiting many times the current age of the universe for it to happen. The real value of the Cosmic Anvil hypothesis isn't in fear-mongering. It's in what it teaches us about the fundamental nature of reality. It forces us to ask profound questions. How stable is our universe really? Are the constants of nature truly constant, or are they just local variables? By contemplating these extreme edges of physics, we better understand the miraculous, delicate balance that makes our peaceful, predictable existence possible. We're not just looking for monsters in the dark, we're learning to appreciate the fragility of the light. Now I want to hear from you. After everything we've explored, the warping of time, the unraveling of matter, the very laws of physics rewriting themselves, what do you think a dimensional collapse would truly look like from the inside? Would it be a silent, instantaneous flicker into a new state of being, with no one left to even remember the old universe? Or would it be a violent, chaotic storm of sensory overload, a final moment of cosmic agony as reality itself comes undone? Perhaps you have a completely different theory. Maybe these events aren't endings at all, but cosmic rebirths, and what we perceive as collapse is actually a transformation into something beyond our current comprehension. Drop your thoughts in the comments below. I read every single one, and your ideas are genuinely fascinating. What's the most creative or terrifying outcome you can imagine? Let's get a conversation going about the ultimate fate of everything. Looking ahead, the search for evidence is pushing scientists to design tools that can perceive the universe in completely new ways. We're moving beyond simply building bigger telescopes to see farther. We're engineering instruments to sense the invisible architecture of reality itself. One of the most anticipated projects is the Laser Interferometer Space Antenna, or LISA, a revolutionary gravitational wave observatory planned by the European Space Agency. Instead of being confined to Earth, LISA will consist of 3 spacecraft flying in a perfect triangular formation, millions of kilometers apart, connected by incredibly precise lasers. This giant, orbiting ear will be uniquely tuned to the low-frequency hum of the cosmos, the exact range where a sustained, anomalous rumble from a persistent dimensional instability might be detected. While current observatories like LIGO catch the brief chirps of black hole mergers, LISA could listen for the continuous drone of a cosmic fault line grinding away over eons, a sound that would be the unmistakable signature of reality under profound stress. On the ground, the quest continues within the realms of the incredibly small. Particle colliders like the Large Hadron Collider were built to discover new particles, but analyzing their data can also reveal the subtle fingerprints of extra dimensions. One tantalizing prediction is that if these hidden dimensions are real and accessible at high energies, colliders might produce particles that seem to simply vanish, carrying energy away into a realm we cannot perceive. It would be the ultimate magic trick, energy disappearing without a trace, not because of a detector error, but because it literally exited our dimensional plane. Future colliders, designed with energies far beyond our current capabilities, could be explicitly configured to probe this possibility. They might even create microscopic black holes or fleeting gravitational instabilities, offering us a controlled, miniature glimpse into the mechanics that could be governing the largest-scale events in the cosmos. The hunt also extends to the farthest reaches of space with a new generation of telescopes. The James Webb Space Telescope has already transformed our view of the early universe, but its successors will be tasked with an even more precise mission: creating ultra-detailed maps of the cosmic microwave background. The goal is to find new, even more subtle anomalies, perhaps a specific pattern of polarization or a temperature distribution that simply cannot be explained by any standard cosmological model. These minute imperfections in the oldest light we can see could be the permanent scars left by a primordial dimensional interaction, a fossilized record of a multiverse event encoded in the universe's first light. Perhaps the most ambitious proposals involve sending physical probes on missions of unprecedented scale. Concepts for interstellar travel, like the Breakthrough Starshot initiative that aims to send tiny, laser-propelled sails to Alpha Centauri, could one day be retargeted. Imagine directing a fleet of nanoprobes on a centuries-long journey toward a gravitational anomaly like the Great Attractor. While we wouldn't live to see the data, such a mission would be humanity's ultimate philosophical and scientific test of a hypothesis, a message in a bottle sent to the edge of a cosmic mystery. These probes would be equipped with sensors designed not just to map planets, but to perform the most fundamental physics experiments imaginable, constantly checking if the local speed of light or the strength of gravity remains constant as they approach the epicenter. Finding that these constants actually change would provide the first in situ confirmation that the laws of physics are not universal, but local and fragile, forever altering our understanding of our place in the cosmos. So let's piece together the evidence we've gathered. It starts with the gravitational anomalies, the cosmic currents we cannot see but can most certainly feel. The Great Attractor is the prime example, a gravitational vortex of impossible strength with no visible source massive enough to account for it. We feel its pull across millions of light years, a silent, invisible hand guiding the motion of our entire galactic neighborhood. This isn't just a missing object, it's a discrepancy in the very force of gravity itself, a signature that suggests the rules are different there. Then we have the strange, source-less gravitational waves, ripples in spacetime that arrive without the telltale chirp of a black hole merger. These are murmurs from the void, tremors that hint at events not involving colliding objects, but perhaps a sudden, violent reconfiguration of spacetime's geometry. Beyond gravity, the high-energy universe offers its own clues. We detect beams of radiation and cosmic rays with energy levels that defy explanation. There is no known engine in the cosmos, no pulsar or quasar that could possibly accelerate particles to such velocities. It's as if the universe itself is focusing and amplifying energy through a lens we cannot see, a lens that could be formed by a profound local distortion in the fabric of higher dimensions, bending the paths of these particles and supercharging them in ways our standard models simply cannot account for. Perhaps the most haunting evidence is written in the oldest light we can see, the cosmic microwave background. The cold spot is not just a statistical fluke. It is a vast, circular region of space that is significantly colder than it should be, a feature that all conventional explanations, like a giant cosmic void, have failed to adequately explain. It stands as a chilling anomaly on the map of the infant universe, a shadow that some theorists believe could be cast by a region where light lost energy as it traveled through a patch of distorted, unstable spacetime. Alongside it, the strange large-scale alignments in the polarization of this light, the so-called axis of evil, suggest a fundamental asymmetry in the universe, a preferred direction that should not exist. This could be the faint imprint of our universe gently brushing against another brain in the multiverse, a lasting tilt in reality's foundation. And finally, we have the theoretical models themselves. This isn't just wild speculation, it's a hypothesis grounded in a century of mathematical exploration, from Kaluza and Klein's fifth dimension to the intricate landscapes of string theory and M-theory. The math not only allows for the possibility of dimensional collapse, in some scenarios it almost demands it. The equations describe how a higher dimensional instability would manifest in our three-dimensional world, as immense phantom gravitational fields, bizarre particle radiation, and distortions in the flow of time itself. The models provide a unified, elegant framework that could potentially explain dark matter as the gravitational shadow of a collapsing dimension and dark energy as the explosive energy released by that collapse. They turn two of cosmology's greatest mysteries into two sides of the same incredible coin. When you step back and look at this entire mosaic of evidence, the unexplained pulls, the anomalous waves, the impossible energies, the primordial scars, and the predictive math, a pattern begins to emerge. Individually, each piece is a curiosity, an outlier that could perhaps be explained away, but together they form a compelling and frankly unsettling picture. They point toward a universe that is not the static, stable stage we once imagined, but a dynamic and potentially volatile structure whose deepest foundations might be subject to change without warning. The Cosmic Anvil remains a hypothesis, but it is one that is increasingly difficult to ignore, a theory that challenges us to question the very nature of reality itself. Yet as we pull our gaze back from these staggering possibilities, we find ourselves returning to a simple, profound truth. The universe is, and always will be, the grandest mystery of all. What we know is a single star in a galaxy of unknowns. The Cosmic Anvil, whether it proves to be a real phenomenon or a fascinating theoretical stepping stone, reminds us that the cosmos is not a static painting to be understood, but a living, breathing story that we are only just beginning to read. Every discovery peels back one layer, only to reveal another, more intricate one beneath it. This isn't a cause for frustration, but for celebration. It means the journey of discovery never truly ends. There will always be another horizon, another question, another whisper from the dark urging us to look closer and think deeper. Your curiosity is the most vital part of this entire endeavor. The questions you hold, the awe you feel when you look up at the night sky, that is the engine of exploration. Keep asking, keep wondering. Let these mysteries ignite your imagination and remind you that we are all part of this incredible, ongoing human project to understand our place in the vastness. The conversation doesn't end here, it continues with you. I am genuinely eager to hear your perspective on all of this. What part of this cosmic mystery resonated with you the most? Do you think the evidence points to a volatile, changing universe, or do you believe our reality is fundamentally stable? Share your thoughts, your own theories, and your biggest questions down in the comments. Let's keep unraveling this mystery together. If journeys into the deepest unknowns of space and time are what fuel your imagination, then you're in the right place. This channel is dedicated to exploring the furthest edges of what we know and what we can only dream of. To make sure you never miss out on our next adventure into the cosmos, be sure to hit that subscribe button and tap the bell so you're notified every time we drop a new video. We have so much more to discover together. Thank you for joining me on this incredible ride to the edge of reality. Stay curious.